Okay, so we're continuing our discussion on how to identify and recognize acids and bases. And we've seen that H is connected to an electronegative atom in a polar bond, can be an acid. But another situation, another group of acids that we have are what are called oxy acids. And so as you might guess, an oxy acid is where oxygen is involved. And so in this case, it's when you have an OH group, which means that you have an H directly bonded to an O. And then that O is bonded to the rest of the atom. A lot of time there's a carbon or nitrogen or something here. But whenever you have that situation, you would have what's called an oxo acid. So here are some examples of the oxo acids. You can look at the structure down here in the pictures. You see there's our H directly bonded to the O. And then the O is bonded to, in this case, a Cl. So that would be an example of an oxo acid. Here's another one, HOI. Again, the H is directly bonded to the O, so there's my OH group, and the O is bonded to the other, in this case, just a single atom. So that qualifies as an oxo acid. And if we want to compare the strengths of these guys, maybe we're looking at these two guys down here, want to figure out, well, who would be the stronger acid? Well, remember, the strength of the acid depends first on the bond strength. And in this case, this would be a tie. The H is bonded to the O here. The H is also bonded to the O on the other one. So bond strength is a tie. So what we have to do is look at the rest of the atom. And remember, the other question is, all right, well, when that H leaves, how well can the rest of the molecule handle that extra electron that it gets left behind? So if we look at these guys, that's a function of the electronegativity. Now, H's are bonded directly to an O, so they're both a tie in terms of who the H is directly bonded to, both in bond strength and in electronegativity. But if we look at the rest of the atom, we see that there's a difference here. The chlorine has an electronegativity of 3.0, whereas the iodine is only 2.5. So that means if this H were to leave here, the rest of this molecule can handle that extra electron better than if this H were to leave. Because the iodine has a lower electronegativity, it can't handle that extra electron as well. So that means that if we look at the strengths of our acids, we see that the HOCl, now they're both weak acids, but the HOCl is a stronger acid to the -8th power versus the HOI to the -11th. So if you have an oxo acid and we want to predict the strength, they're all going to be H's to O's, so that part's a tie. So what we need to do is just simply compare the electronegativities on whoever that O is bonded to. The higher electronegativity is going to be the stronger acid in this case. So what are some other factors? Well, if we look at these examples, these are all oxo acids. We have the H bonded to an O. So if we try to figure out, well, who's going to be stronger in this case? Well, that part's a tie. So then we look at, well, who's the O bonded to? Well, that's Cl. That's also Cl. In fact, every one of these has the O bonded to the Cl. So we're a tie in terms of the electronegativity of who the O is bonded to. Well, we want to consider that molecule as a whole. Now, notice the difference between all these guys is the number of oxygens that are bonded to the chlorine. So this chlorine has no oxygens bonded to it. This one has one, this one has two other oxygens, and this one has the three other oxygens bonded to it. So remember, oxygen is highly electronegative. That means it attracts electrons, it likes electrons. So we're concerned with when the H leaves, how well can the rest of that molecule handle the extra electrons? Well, the more oxygens that you have, the more it can spread that extra electron out. So this, when the hydrogen leaves and it leaves that electron behind, this part here, we've got the 1O, which can help handle that extra electron better. So this is a stronger acid than this first one because you have an O attached to that central atom. And as we move down this way, now we have two extra oxygens, which can help handle that extra electron. And then we get down to the very last one here, the perchloric acid. You have lots of extra oxygens around, which can handle that extra electron. So we can see that the strength changes quite significantly. I mean, here, this is a pretty darn weak acid. Now we're getting significantly stronger. It's still a weak acid, but it's a pretty strong weak acid. And when we get to these guys, these are actually both considered strong acids, where they would 100% dissociate. So that's our factors. Okay, if that's a tie, look at, well, how many oxygens are attached to the central atom. The more that are attached, the stronger the acid is going to be. In fact, a good rule of thumb, okay, if you have an acid that you have never heard of before and you're looking at the formula for that acid, if it is an oxo acid, look at how many oxygens are attached. And here's the rule. If there are at least 2 more O's than ionizable hydrogens, then it's going to be a strong acid. So if we look at this example up here, we only have 1 ionizable H, and there are 4 O's in this formula. So there's lots more O's. The rule definitely applies here, so that is a strong acid. This one, you have 1 H and there's 3 O's, so that we have exactly 2 more O's than ionizable H's, so that is a strong acid. But this one, we have 1 H and only 2 O's, so there's only 1 more O. So the rule does not apply to this guy, and so we see it is not a strong acid. So if we think about H2SO4, we know that's a strong acid. We memorize that one, but if you look at it, now that one has 2 ionizable H's, but it has 4 O's. And so therefore it does have 2 more oxygens than ionizable acids, so it is a strong acid. Now compare that to another acid that we know, sulfurous acid, and that has 2 ionizable H's, but it only has 3 O's, so there's only 1 more. So there's not enough O's to be able to handle the extra electrons quite as well, and so that is not a strong acid, that is a weak acid. So this is a good rule of thumb to keep in your back pocket and pull out when you need to. You can look at a formula and you can say, oh, that's definitely going to be a strong acid if it's got the 2 more O's than ionizable H's. Okay, so here's a couple questions for you. So take a minute and compare these. Who's going to put these in order of increasing strength? All right, so if you got this correctly, you might remember, what do we look at? First factor we looked at is bond strength. Remember, the stronger the bond, the weaker the acid is going to be because that H has to leave. And so in this case, these are all easily comparable in terms of bond strength. This is the smallest of all of the atoms. So that means this is going to be a stronger bond, which means this will be the weakest of all of those 3 acids there because of the stronger bond, whereas the iodine is bigger, and so that's going to have the weaker bond. So that means that's going to be the stronger of the acids because this H can leave more easily. Okay, and you might remember this chart from our notes, and that's why we have this pattern. As we go down, they get more and more reactive if we're staying in the same column. Okay, so here's another question for you. So go ahead and rank these in order. All right, so again, trying to figure this out, these are all oxo acids. There's all an HO bonded to something. And in this case, we want to look at the central atom, and we might even be pretty familiar with water. We know that water is a very weak whatever it is. It's generally neutral, but it can be a weak acid, a weak base. So we might even think, okay, this guy's very, very weak. That'd probably be the lowest out of the bunch. So if we look at these other guys, okay, you have an H bonded to an O. In this case, the O is bonded to the Se. And I'm not drawing all the double bonds and electrons here. We'd have some. So in this case, we've got that example. And in this example, you've got your He with your OH group on that. But you've got 3 other oxygens around that. So we can see this part's a tie. They both have H bonded to O. So the O is a tie. So the bond strength is a tie. The immediate atom, they're both oxygens, so that electronegativity is a tie. In fact, the oxygen in both cases is bonded to the same guy, so the electronegativity there is a tie. So our question is, who can handle if the H leaves? Who can handle that extra electron better? Well, here you have 3 O's, and here you have 4 O's. So as we've seen, the more O's, the better we can handle. In fact, our rule of thumb applies to this guy. We've got 2 ionizable H's, 4 O's, so this has 2 more O's than ionizable H's, so we know that is going to be a strong acid. We would expect that to completely dissociate. This one does not fit that rule. There's only 3 O's left, so that is going to be a little bit weaker. And then the water, you have a higher bond strength there and everything too, so that's going to be the weakest of all those 3. So a couple other quick things in terms of some typical acids that you might see in regular chemistry as well as in biology as well. In fact, some of you may have heard of this from biology. You might have heard of a carboxyl group in biology class. If not, it's a famous organic chemistry group, and that group tends to be an acidic group. So we have a category of acids called carboxylic acids. And here's your generic formula for that. So a carboxylic acid is one where you have this OH group bonded directly to a carbon, and that central carbon has a double bond to another oxygen. So a lot of times we call them the COO group because it's often written as COOH. And this R stands for just the rest of the molecule. Okay, it might, if the smallest one, this one might just be a hydrogen, but we could have more carbons and all kinds of other things over there. But anytime you see this specific type of a grouping, an OH bonded to the C and that same C double bonded to an O, that is qualifies as a carboxylic acid. And this H right here has the ability to leave. That's my acidic hydrogen, because we have the two oxygens here that can handle that extra electron. They don't tend to be strong acids, but they definitely are acidic. So keep an eye out. That pops up in a lot of compounds. Here's some examples of some acids. These are all carboxylic acids. So you see here, formic acid, there's our simplest of all the carboxylic acids. But if you look, you've got the carboxyl group. In fact, you can have more than one. Citric acid, our lemon juice and orange juice acid there, we've actually got 3 carboxylic groups. So all 3 of these are acidic hydrogens. So that hydrogen can leave very easily, this one. So this actually has 3 ionizable hydrogens on the citric acid. And then you've got some other things, the active ingredient in aspirin, acetylsalicylic acid, which is just fun to say. But there's your carboxyl group there, and some of the other ones there. You should be able to identify the carboxyl groups in those. Acetic acid, the vinegar, most famous. That is actually a type of a carboxylic acid. And there, so this one H, this is the ionizable H. These H's do not leave. So acetic acid only can donate one H because that's the acidic hydrogen. Now, talking about bases and some common bases that we might run into. A base, remember our definition of a base is they're proton acceptors, or the Arrhenius definition is that they don't dissociate in water to make hydroxide. And what you'll typically find on bases is that if you think about the Bronsted definition, they're proton acceptors, which means bases often will have either a negative charge to them or they might have unshared pairs of electrons. And those unshared pairs of electrons, if I have a proton, that provides a nice docking station for that proton. So either things with negative charge, and usually things with negative charge that have that unshared pair of electrons, those we're typically going to find to be bases. In fact, yeah, so there's another picture of that. So bases, we have 2 major categories of bases. We have strong bases, which all of our Arrhenius bases would typically be strong bases. If you have a water-soluble compound that has hydroxide as the negative ion, we're used to recognizing those as bases. But also if you have oxygen as the negative ion. Now the key is here it has to be a water-soluble compound with oxygen. A lot of those are not, but it has to be someone who's soluble. So who's going to be very soluble? Well, remember the group 1 elements, potassium, sodium. We've memorized on our solubility table that potassium compounds are pretty much always soluble. Sodium compounds are pretty much always soluble. So if you've got a group 1 hydroxide, like KOH, then it is going to be a strong base because it completely dissolves and we're going to have lots of these hydroxides. So also if you have a group 1 oxide, potassium oxide, sodium oxide, those are going to be soluble as well. And so those things are going to be strong acids. So group 1 or group 2, those first 2 columns on the periodic table, any hydroxides or oxides from those guys will automatically put into the strong base category. Now the weak bases are typically going to be structures where we have a nitrogen on it and where that nitrogen is making 3 bonds and the nitrogen has an unshared pair of electrons on it, like we saw in that earlier picture. So that is going to be a docking station